So back to the paper again. We did till question number 20. Now it is 21. Obtain the expression for energy stored in a capacitor connected across a DC battery. Hence the energy density of the capacitor. So obtain, this is a very important question. This is a 3-mark question. Obtain the expression for energy stored in a capacitor and find energy density. Right. See this, I have a capacitor here. This is a capacitor, okay? I'm connecting a cell across this and a switch. So the moment you start, the moment you switch the circuit on, current starts flowing or charge starts flowing and the capacitor starts getting charged. All right, give me a second, please. So when you connect the capacitor to the cell and when you switch the circuit on, charge begins to flow and the capacitor starts getting charged. How is the charging done? Look at this. This is positive terminal. Positive terminal has the capacity for pulling electrons, right? Positive can attract negative. So this positive terminal will attract electrons one by one. One electron is gone. It is one positive. One more electron is gone. Again positive. Third electron is gone. Positive. Fourth electron is gone. Positive. At the very same instant, electrons are repelled by the negative terminal. That is how the circuit is completed. So electrons are released one by one. One, 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 one. And this is how charging takes place. Okay. So we have taken a capacitor. We connected this to a cell and a switch. And then when you switch it on, charge begins to flow. Charging is a slow process. It's a time-consuming process. Okay. It's a time-consuming process. There is an equation for charging which is not there in your syllabus. This is how it is written. 1 minus e raised to minus CR into t. Right. That is how you take for a CR circuit, the charging of a capacitor. But don't worry about it. That is not there in your syllabus. So just take it this way. The capacitor starts getting charged. How is it charged? Electrons are taken one by one by the positive terminal. At the very same instant, electrons are released from this side as well. So the capacitor slowly starts getting charged. Now, what is the equation for potential difference? Do you remember? Potential difference was written as Q by C. Q by C. Okay. And there was one more equation. W is equal to. Potential difference was written also as W divided by Q. Do you remember the definition of potential? It is the work done. It is the work done to bring a +1 coulomb from infinity up to the point. Work done to bring a +1 coulomb from infinity up to the point. So work done per charge is potential. You have seen this many times this year, right? Potential is work done per charge. So I'm going to find out dW now. What is dW? Work is Q into V, right? V into Q. So dW will be what? V into dQ. What have I written? I've written the small work done. Small work done for what? Small charge transfer, small charging. Why do I take differentiation here? Why do I take small charge here? Because the charging process is a slow process. It takes time. Okay, it happens over a long time. So what you do is you'll take a small charging and then you'll integrate it from 0 to final position, final time, right? That is what you've been doing, right? So I'm repeating, V is equal to W over Q. This is the definition for potential. Potential is defined as work done per charge. If you cross multiply, you get work done is equal to Q into V, Q into V. But I'm finding the small work done here. Small work done is potential into small charge. So I can put it here, dW is equal to, what is V? V is there, Q by C into dQ. Now this is only the small work done. So you can find the total work done just by integrating this. Integrating Q by C dQ. From where to where? You started off with the 0 charge and you ended up with maximum charge. Okay, so 0 charge is the charge that you started with, and this is final charge is capital letter Q. So let us integrate this. What do we get? 1 by C into. What is integration of Q? Q raised to 1 is Q square over 2. Q square over 2. From 0 to capital letter Q. Okay, that is how the limits are given. Then 1 by C into, you give the upper limit. In place of small q, you should be writing Q square by 2 minus, in place of Q, you should be putting 0. But there is no point in putting it. So I can keep it like this. That is Q square over 2C. This is the work done, which is stored as potential energy inside. U is equal to Q square by 2C. This is the first part of the question. I'll tell you the associated questions as well. V is equal to Q is equal to Q square by 2C. Did you understand this? Now we have Q square by 2C. This is the potential energy stored in the capacitor. Okay, there are other expressions as well. You know, you can modify this equation. You can modify this equation by putting the value for C. And you have three equations. You're getting three equations this way. One is U is equal to Q square over 2C. Second one is half CV square. Third one is half QV. These are the equations for energy stored in a capacitor. Q square by 2C, half CV square, half QV. Okay. And the second question that they ask is energy density. Energy density. Now, there was one question in one of the board examinations. Where is this energy stored? Where is this energy stored in a capacitor? The energy is stored. This is positive plate of the capacitor and this is negative plate of the capacitor. And you know the electric field here is 0. Electric field here is 0. Electric field here is sigma by epsilon 0. We have even proved this many times. You remember? That is a very important board question. Last year it was asked. Forum paper question. Many times asked. Outside the field, plate, outside the plate, the field is 0. Outside the plate, the field is 0. In between the plates, the field is sigma by, this paper had this question. We did this in the last class. You remember, sigma by epsilon 0 is the field. And the previous board question was like, where is the energy stored? The energy is actually stored as potential energy in the electric field shown here. Electric field is from positive to negative. Electric field is from positive to negative. So in between the plates, there's a space where the energy is stored. Okay, the energy is stored in the space in between the plates, in between the plates. You're going to find the energy density now. What is energy density? Energy by volume. Because density is mass by volume, then energy density must be energy by volume. Repeat after me. Energy density is energy by volume. Normal density is mass by volume. So energy density must be energy by volume. Total energy stored in here divided by volume of the system. So what is energy? I can put half CV square. What is volume? Volume is area into distance. Look at that. Area of one plate is A and the distance of separation is D. Area into distance will give you the volume, right? Oh, tell me what. If you're sitting in a room right now, right? On the left side, there is a wall. The distance between the walls is D. How do you find the volume of the room? Area of one wall multiplied by the distance between the walls will give you the volume of the room. Am I correct? Am I correct or not? Tell me, please. How do you find volume of a? How do you find this? Looks like a room, doesn't it? So energy is Q square by 2C or half CV square or half QV. Next is to find the energy density. Energy density means energy divided by volume. Energy is half CV square. Volume is area into distance. So let's put the values here. Half into, what is C? Epsilon 0 A by D, capacitance of a parallel plate capacitor, into, what is V? Electric field into distance. Do you remember this? V is, electric field was written as voltage by distance, dV by dr, dV by dr. Do you remember that? E is equal to V by D. Electric field is gradient of potential, V by D. So to be precise, the equation looks like this, minus dV by dr. Anyway, electric field is negative gradient of potential. Anyway, electric field is equal to voltage by distance, voltage by distance. So let's cross multiply. V will be E times D. That is what I've done here, E into D, divided by A into D. So let us cut A with A and then D with D, 1D with 1D. So what do we get then? Half epsilon 0 E square. That is the expression for energy density. Did you understand? Now, one important question here is common potential question. This is very, 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 very important. Many times asked. We have done this at least 10 times in class. Okay. Common potential question. I have a capacitor here. Capacitor is C1 and it is raised to potential V1. How do you raise it to potential V1? You connect it to a battery and you charge it for some time. Okay. See, a capacitor is C1 and it is connected to a battery and it is charged to full. It is V1 now. Potential is V1 now. You take another capacitor C2, charge it to V2, and then you connect them together using a wire. What will happen now? It's like these are like two buckets of water. Okay, one bucket of water with greater level, higher level, and another bucket of water with a lower level, like this. What if you connect them through a pipe? Water flows from higher level to lower level till both have same level. Same way here, charge flows from higher potential to lower potential till both attain a common potential. Okay, so what have I done here? I've taken two capacitors. The capacitors have different potentials, okay, different values. So C1 and C2, the potentials are also different. They are raised to different potentials. Cool. Okay, so they are like two different water levels, and you're connecting them together using a wire. What's happening now? Charge flows from higher level, higher potential to lower potential till both have a common potential. What is the equation for common potential? Important numerical. C1V1 plus C2V2 by C1 plus C2. C1V1 plus C2V2 by C1 plus C2. That is how you take common potential. And this is a common potential in the end, like common level. Similar way, and another thing is there, the energy loss during this. Energy loss during this is given by half into C1 C2 by C1 plus C2 into V1 minus V2 the whole square. This equation very important. Chapter and exercise has a question on this, and even last year this was the first question in JEE examination, repeated competitive examination question also. These two equations are not explicitly given in textbook, but you have to learn. These are supposed to be the most important equations in capacitance, even though not given. Delta U is what? Energy lost. Energy lost upon sharing. Energy lost upon connection is half into C1 C2 by C1 plus C2 into V1 minus V2 the whole square. You just have to put the capacitance values and potential values. Okay, and in some of the cases they'll say like one capacitor is uncharged. One of the capacitors is uncharged. Uncharged means that capacitor is to be taken at zero potential. So you have to put 0 for one of these values, V1 or V2. Okay, it doesn't matter much because anyway it's going to be squared. So even if the other one is minus, that will become positive in the end. Okay. So if one of the capacitors is given to be uncharged, they'll say like uncharged. They all the time they give such questions. One of the capacitors is uncharged. If that is uncharged, that means potential is 0 for that capacitor. So you put it across and find the value. Okay. And the third question is, in energy stored, what was the equation for energy stored? Energy stored was half CV square or half QV or Q square by 2C. What is the work done by cell in this case? In these cases, work done by the cell. Okay, I take a capacitor and I connect a cell. Okay, what is the work done by the cell? Work done by the cell is what? Double of the CV square or QV or Q square by C. It's actually double of this energy stored. So half the energy is stored. Where is the other half gone? See, these are actually works done by the cell. So work done by the cell is CV square. But energy stored is only half CV square. Where is the other half gone? That half is lost on connection wire as heat. Work done by the cell is QV. While the capacitor gets only half QV. Where is the other half gone? The other half is lost as heat on the connection wire. Or work done by the capacitor, work done by the cell is Q square by C. But here it is only Q square by 2C. Where is the other half? The other half is on connection wires, lost as heat. Okay, this is a very important question. They'll ask you to find the ratio of work done to energy stored. Work done to energy stored is 2. Okay, the ratio is work done to energy stored is 2. It's a competitive examination question as well. Work done to energy stored. Work done is CV square, but energy stored is half CV square. So the ratio is 2. And the fourth possible probable question is, draw the graph of Q against V. What sort of a graph do we have? Straight line, because Q is directly proportional to V. If you remember, Q is directly proportional to V. Do you remember this? Q is directly proportional to V. Straight line graph. So the graph is a straight line. And they'll ask you to find either the slope of the graph or the area under the graph. What is the slope? I'll draw it here. Okay, so that ratio is important. W divided by Q, that is equal to 2, that ratio. And then this is Q against V graph. Q is directly proportional to V. So if If Q and V are directly proportional, the graph must be a straight line, straight line. I'm going to take a triangle here and take tan theta. That is called slope. Slope. Slope is tan theta, slope is M. M is tan theta. What is tan theta? Opposite side by adjacent side. Opposite side, if you come here, it is Q by adjacent side is V. Q by V is capacitance. So slope of QV graph is capacitance. What is area under the graph? Area, it looks like a triangle, right? Triangle. What is area of the triangle? Half into base into height, half QV, which is energy stored. Energy stored. Okay, so first question is what? You'll be asked to draw the QV graph. Q against V graph. The graph is a straight line as it is direct proportionality. And then slope of the graph. Slope of the graph is always Y variable by X variable. That is opposite side by adjacent side. Opposite side Q, adjacent side V. Q by V is capacitance. And second is area under the graph. Area under the graph is that of a triangle. For a triangle, the area is half into base into height. So half into base is V. Height is Q, half VQ. Half VQ is energy stored in the capacitor. And this is a previous board question. Find the ratio of capacitances of A and B. A and B. How do you find this ratio of capacitance of A and B? A and B. Ratio of capacitances of A and B. Find the ratio of capacitances of A and B. So how do we do this? How do we do this? Capacitance of A and B. Capacitance of A is tan of theta A. Tan of theta A. So tan of 30. Tan of 30. Tan of 30 is 1 by root 3. Second is CB. That is tan of theta B. That is tan of 60, which is equal to root 3. So CA divided by CB is 1 by root 3 by root 3. So that is 1 by 3. The ratio is 1 by 3. Did you understand this? 21 has an OR question. Derive the expression for the torque acting on an electric dipole, which is held in a uniform electric field. Identify the orientation in which the dipole is in stable equilibrium. You remember this? We did this in magnetism as well. So this is the electric field, uniform electric field. Look at this, uniform electric field, uniform electric field. I keep a dipole here. This is the dipole. Okay, dipole has how many charges? Plus Q here, minus Q here. Okay, and then this charge has a force to the right. There the force is to the right. Why is the force to the right? F is equal to QE. Because there must be some positive plate here and there must be some negative plate here, because lines always go from positive to negative. So there is an invisible plate, positive plate here, another invisible plate, negative plate here. The lines are going from positive to negative. And as you can see, this positive plate is repelling this plus Q to the right with the force QE. At the same time, the positive plate is attracting this minus Q to the left with the force QE. Now these guys together will create a couple or torque. How do you find the torque? You have to complete this diagram. You have to complete this diagram. And this angle is theta. This length is 2L. Length of the dipole is 2L. Opposite side is X. I take the opposite side as X. And then I take sine theta in this triangle. What is sine theta? Opposite side X divided by hypotenuse 2L. Cross multiply. X will be 2L sine theta. The question is to find the torque, and torque is force into perpendicular distance. One of the forces into perpendicular distance. One of the forces, one force is QE, the other force is also QE. So one of the forces means QE into perpendicular distance. Look at the perpendicular distance, that's X. Into X. That is QE into X is what? 2L sine theta. 2L sine theta. And then if I take Q and 2L together, that will be PE sine theta. Tau. So vector tau is equal to vector P cross vector E. Did you understand this? Vector tau is equal to vector P cross vector E. Did you understand till this point? See, we have a dipole that is placed in a uniform electric field. This is a uniform electric field. How do we know if it is a uniform electric field? All the lines are straight. All the lines are parallel. They are equidistant as well, equidistant. And as you can see, I can put a plus plate here and minus plate here because the lines are going from positive to negative. Okay. And then in here, I'm placing a dipole. This is a dipole, putting a dipole over here, okay? This is one charge plus Q. This is another charge minus Q. A dipole is a system of two equal and opposite charges. One charge is plus Q, the other charge is minus Q. And then what's happening here? This plus plate is repelling plus to the right. This plus is repelled to the right with the force QE. This minus is attracted to the left with the force QE. So there are two forces basically, right? Two forces, right? These two forces will create a couple or a torque, you know, by which it can rotate. This guy is going here, this guy is going here. So it is rotating, the dipole is rotating. Okay, not a complete rotation, but anyway, it gives a rotational motion. So in this triangle, I take sine theta. What is sine theta? Opposite side divided by hypotenuse, to x divided by 2l. Cross multiply x is equal to 2l sine theta. Then torque is defined as what? This is something you learn in first year classes. One of the forces multiplied by perpendicular distance. One of the forces. What are the forces here? One force is QE. The other force is also QE. So one of the forces is QE into perpendicular distance. Look at this. This is line of action for the first force. This is line of action for the second force. Okay. Line of action. Look at the line of action. The perpendicular distance is x. Look at these lines, you know, and the perpendicular distance is x. It's not this distance that is to be taken. X. X is what? Cross multiply 2l sine theta. 2l sine theta. So Q into 2l is what? P. So tau is equal to P sine theta. That is vector tau is equal to AB sine theta is what? A cross B. AB sine theta is A cross B. So vector tau is equal to vector P cross vector E. And in one of the foreign paper examinations, there was a question. Identify the perpendicular pair of perpendicular vectors. Identify the pair of perpendicular vectors here. Can you tell me which one? You know the cross product. You know how cross product is written? C is equal to A cross B. How is it taken? How is it taken? C is equal to A cross B. How is it taken? If this is A, this is B, where is A cross B? This is vector A, vector B. Where is A cross B? A cross B is C. A cross B is C, that is going into the board. You know how to take the cross product direction? How do we take the cross product direction? How do we take the cross product? Do you remember? You put a screw here. You put a screw here at the junction, no? And turn the screw in clockwise direction from A to B. From A to B, you have to turn the screw. Where is the screw heading? The screw is going into the board. In the whole world, wherever you go, if you put a screw here and turn it in the clockwise direction, that will definitely go into the board. Okay, that is called right-handed screw. Right-handed screw. If you turn it in the clockwise direction, the screw is going into the board. So my point is, A and B are on the board, while A cross B is into the board. A is on the board, B is on the board, A cross B is into the board. So I could say like A cross B is perpendicular to both A and B. A cross B, that is C is perpendicular to A and B. Okay, so here tau is perpendicular to what? I could say tau is perpendicular to P. Tau is perpendicular to E as well. So the previous board question was to identify the pairs of perpendicular vectors from this. Identify tau is perpendicular to P, tau is perpendicular to E. Why? P is on the board, E is on the board, while torque is into the board. Did you understand this now? There is one more question here. They are asking you to get the condition for equilibrium. I'll tell you what sort of equilibrium you have. I'll write down few equations. See this now? We did this question in magnetism and matter a few days back. Torque was written as what? P is sine theta. Right. For equilibrium, what do we need? Equilibrium means what? Torque has to be zero. Equilibrium implies that torque is equal to zero. There are two types of equilibria. One is translational equilibrium, straight line equilibrium. That happens when force is zero. But here we are talking about rotation. So torque has to be zero. If you want the for rotational equilibrium, there are two types of equilibria. Like I said, one is translational equilibrium, for which force is equal to zero, net force equal to zero. But here we are talking about rotational equilibrium. Torque is equal to zero. Torque is equal to zero. That is a condition. That means what? PE sine theta has to be 0. But P can never be 0. E can never be 0 either. Then who can be 0? Sine theta can be 0. That happens under two conditions. Hope you remember. One is theta is equal to 0. Second is theta is equal to 180. Theta is equal to 180. Okay, these are the conditions under which, that's a very, very, very important question. Conditions under which torque can become equal to 0. Look at that. I'm going to find the potential energy now. Do you remember the equation for potential energy? Minus PE cos theta, minus PE into cos 0. That is minus PE. Minus PE means it is minimum energy. Minimum energy. Minimum energy is what? Stable equilibrium. Stable equilibrium. That is stable equilibrium. Okay. How about right side? Potential energy is minus PE into cos 180 there. Cos 180 is what? Minus PE into minus 1. That is plus PE. Plus PE is what? Maximum energy. That is unstable equilibrium. Unstable equilibrium. So there can be stable equilibrium or unstable equilibrium. I'll explain that one more time. Second question is regarding equilibrium. What is equilibrium? I told you there are two types of equilibria here. One is linear equilibrium, translational equilibrium. That happens when force is equal to 0. You don't have to bother about it, but instead there is another kind of equilibrium called rotational equilibrium. Rotational equilibrium. So that happens when torque is equal to 0. And when torque is equal to 0, that obviously means PE sine theta is equal to 0. But P can't be 0, E can't be 0, so sine theta alone can be 0. That is possible when theta is either 0 or theta is 180. Sine 0, 0, sine 180, 0. So theta is 0, theta is 180. So potential energy is what? Minus PE cos theta. That is minus PE cos 0. Minus PE cos 0. Cos 0 is 1. Minus PE into 1. Minus PE. Potential energy is minimum here. This is minimum. And minimum potential energy means stable equilibrium. Theta is equal to 180. You put theta is equal to 180 minus PE into cos 180. Cos 180 is minus 1. Minus or minus plus. Plus PE. Plus PE means it is maximum energy and that is unstable equilibrium. Is that clear? Now, this is another question that can come from this part. This is the uniform electric field. Uniform electric field, like I said once, this has been asked 8 times in entrance examination so far. Right. So this is the charge plus Q. This is the charge minus Q. Here the force is QE to the right. Here the force is QE to the left. What is the force on this dipole? What is the force on this dipole? Take this force and put it at the center of mass. Look at that. Look at that. And take this force, project this onto the center of mass. So I got how many forces? QE to the right, QE to the left. So F net is what? QE minus QE. They are in opposite direction, that is 0. Show that for a dipole placed in a uniform electric field, the net force acting is 0. Previous board question. Okay, show that we have a dipole here. This is a dipole that is kept fair. The dipole is kept in a uniform electric field. So it experiences a force QE to the right, QE to the left. Let us project these forces onto the center of mass. I take this force out and put it here. And I take this force and put it here. They are equal and opposite. They will cancel each other. F net is equal to QE minus QE is equal to 0. So what can you say about this? In this case, F will be 0, torque not equal to 0. Why is F 0? F to the right, F to the left, they being equal will cancel each other. Torque not equal to 0. Torque is P sine theta. So which means what? Here no translational motion. Translation means what? Straight line. No straight line motion because there is no force. There is no force. It won't move anywhere. It will stay there. Translational motion is not there because force is 0. How about rotational? Only rotation. Only rotation will be there. That means the dipole will stay there and rotate like this. Rotate like this. Okay, the dipole can rotate, give a rotation motion, not full rotation though. Okay. Now, what if it is placed in a non-uniform field like this? This is a non-uniform field. Non-uniform field. As you can see, this is my dipole. Right. One force is QE. The other force is QE dash. They are different this time. Why? Because that is a non-uniform field. Non-uniform means the values are different at different places. So let's, like we did here, let's project them onto the center of mass. project the force to the center of mass QE, project this force to the center of mass QE dash. This is QE dash. Okay. Okay, so project the mass, project the forces to the center of mass. What happens then? You can, are the forces cancelling each other there? No, because the forces are in different directions, right? So they can't cancel. They can't cancel. Here the forces could cancel because they were equal and opposite. But here they are not equal. They are not opposite either, right? So they won't cancel. One is QE, the other one is QE dash. They are never going to cancel. So I could say F is not equal to 0, tau not equal to 0. That means there is translational motion plus rotational motion. So the dipole will execute both rotation and translation. So dipole will rotate at the same time the dipole will move in a straight line. So the question is this: a dipole placed in a uniform field experiences no force, only torque. A dipole placed in a non-uniform field experiences both force and torque. Okay, a dipole placed in a uniform field experiences no force, only torque. That means no translational motion, only rotational motion. But if it is placed in a non-uniform field, it experiences both force and torque. So both translation and rotation. Okay. So second question is, show that the net force on a dipole placed in a uniform field is 0. They can ask this for electricity or magnetism. They'll ask this in electrostatics, or they can even ask this in magnetism as well. We did the other day. Did you understand this? Question number 22. Gamma rays and radio waves travel with same velocity in free space. Distinguish between them in terms of origin and main application. Okay. So for this question, the answer was given in a worksheet. You remember there is a tabular column with for every electromagnetic wave, to the right side of which the origin is mentioned and the application is also mentioned. You have to learn those things. Do you have it? Otherwise, I'm sending it right away. Do you have it? The origin and what are the waves here? Gamma rays and radio waves. Gamma rays and radio waves. Gamma rays and radio waves. Wait for a moment, I'll share it. So for 22nd question, refer to the note that I gave. That note covers everything, all types of electromagnetic waves, all electromagnetic waves, their detection, their generation, and their applications. Okay, their generation and how they are generated. Radioactive decay of nucleus. That is how gamma rays are generated. Gamma ray emission, alpha emission, beta emission, gamma emission. That's not part of syllabus anymore, but gamma rays are emitted as a result of what? Gamma rays are emitted by radioactive decay of a nucleus. Okay. Anyway, question number 23. That's an easy one, direct one. But they can ask from any part. Question number 23. Define the term wavefront of a light. A plane wavefront AB propagating from denser medium into rarer medium incident on surface P1, P2 separating two media as shown. Using Huygens principle, draw the secondary wavelets and obtain the refracted wavefront in the diagram. Did you understand the question? Read it again. Question number 23. Define the term wavefront of a light. You know what wavefront of a light? It is the locus of all particles which are vibrating in phase. Locus. You remember what locus is? You learned this in mathematics classes, locus. Or I told you, locus is the system connecting all the points together. Okay. So what is a wavefront? A wavefront is the system of particles in one phase. You know, this is a particle, this is a source, right? Source means source of light. And then there are particles here which are vibrating in phase. Okay, these are connected together. System of particles vibrating in phase. Locus, the system is called locus, L-O-C-U-S. That's a mathematical term. As wavefront is the locus of L-O-C-S, locus of all particles vibrating in phase. And then you should write one more thing there. Phase difference between particles on a wavefront is 0 because they are all in phase. So the phase difference must be what? Phase difference must be 0. Understood this? I'm repeating. What is the question? What is a wavefront for a light? So this is a source of light and the locus of all particles having same nature of vibration. All particles which are in phase are said to be on a wavefront. And on a wavefront, phase difference between particles is 0. Previous question again, because all the particles are in phase. So obviously phase difference must be what? Phase difference must be 0. And the second question is, what are the types of wavefront there? What are the types of wavefront? I'll tell you. One is, what are the types of wavefront? One is spherical wavefront. If the point source of light, if a point source of light is used, the wavefront is spherical. The wavefront is spherical. Look at that. Point source of light is used, the wavefront is spherical. Look at that. Point source, this is point source of light, right? Wavefront is spherical. And if we have a linear source of light, this is linear source of light, right? Linear source of light, the wavefront is cylindrical like this. Okay, cylindrical. Because, you know, if you have a source of light here, you take 1 meter, 1 meter, 1 meter, 1 meter, 1 meter, 1 meter, 1 meter in all directions. 1 meter is a random number, it can be 3 meters. Okay, 1 meter, and all those points are connected together, you're getting a sphere. That is called a spherical wavefront. So this is spherical wavefront. Spherical wavefront. For what? For point source of light. Point source of light. It's a point source of light, like a bulb or something. Look at my fist. This is a bulb. And this is spherical wavefront is for a point source of light. If it is a linear source of light like this is linear source, right? Okay, linear source, like a tube light or something. Slit. 1 point, 1 point, 1 point, 1 point, 1 point. Everywhere, if you consider the points, that becomes a cylindrical wavefront. So this is cylindrical wavefront. Okay, I can draw the rays like this, ray diagram. Rays are always perpendicular to wavefront. So this is spherical wavefront for a point source of light. This is cylindrical wavefront for a linear source of light, straight line. And remember, the wavefront is always perpendicular to the rays, perpendicular to the rays. And there can be a third type of wavefront. What is that? Plane wavefront. Plane wavefront, the rays are drawn like this. You know, these are actually what plane wavefront is. This can become a plane wavefront. This can become a plane wavefront when the source is at infinity. Look at that. How does it become a plane wavefront? It gets bigger, it gets straightened up, right? As you go to infinity, the curvature gets straightened up, right? So that makes it a plane wavefront. So these are the three types of wavefronts. First one is spherical wavefront. That is for a point source of light. Second one is cylindrical wavefront. That is for a linear source of light. Both spherical wavefront and cylindrical wavefront become plane wavefront at infinity. When they go to infinity, they become plane wavefronts. And the other question here is, a ray of light is going from a denser medium to a rarer medium, a plane wavefront. Look at this. This is denser medium, this is rarer medium. This is how the wavefront is hitting, okay? Oh, it is coming from denser, right? It's coming from denser, so I should be drawing it at a greater angle like this. So denser to rarer, this is how it goes. And I need to draw what? I need to draw the refracted wavefront, right? Refracted wavefront. Just follow the rays, that's it. How does the ray will go? It's going from a denser to rarer medium, denser to rarer, away from the normal, rarer to denser, towards the normal. Denser to rarer. Do you remember this from ray optics? Denser to rarer, away from the normal, rarer to denser, towards the normal. Denser to rarer. Look at this. Denser to rarer, away from the normal. Denser to rarer, away from the normal. Then how do you draw the wavefront now? Draw a line from this point to this perpendicular. Right. That will be our refracted wavefront. This is the incident wavefront, okay? Incident wavefront. I can call it AB. And this is refracted wavefront, CD. How do we draw that? From this point, draw a perpendicular here. The point where it hits is C, right? So CD is our refracted wavefront. AB is the incident wavefront. What if it is going from rarer to denser medium? The other way, rarer to denser medium. I'll draw that as well. Rarer to denser. Look at that. This is one line. This is another line. Rarer to denser. What's happening to the ray? The ray is bending towards the normal. There also I can draw a perpendicular, right? So CD is my refracted wavefront. Here it is bending that way. Here it is bending this way. Did you understand? Question number Question number 23, or question is not required. 23, or question is not required. Light from sodium lamp passes through two Polaroid sheets. Polarization is out of syllabus now. Polarization is out of syllabus now. So for question number 23, or question can be scored off. That is not required anymore. Okay. So let's do 24th question, 24th question, 24 and 25. 24. A heavy nucleus P of mass number 240 and binding energy 7.6 million electron volt nucleon per nucleon splits up into two nuclei. Q and R. Repeated question, textbook question. We did this question in class of mass numbers 110 and 130, and binding energy per nucleon is 8.5 and 8.4 respectively. Calculate the energy released in fission. Could you please read that one more time? Read the question one more time. You won't be taking the break then. Okay, we'll go straight away. Right. Question number 24. A heavy nucleus P. A heavy nucleus P of mass number 240 and binding energy per nucleon 7.6. Okay. Splits up into Q and R. Splits up into Q and R. Q and R of mass numbers 110 and 130. And binding energy per nucleon 8.5 and 8.4 million electron volt. Calculate the energy released in fission. I'll do this question first, then I'll give you the related questions. What is the question? A heavy nucleus P. This is actually fission process, right? Read it again. A heavy nucleus P. This is a heavy nucleus P, like uranium. Uranium is split up to get barium and krypton. Uranium 235 is bombarded with a neutron. You remember fission process? A uranium nucleus, heavy nucleus such as uranium, is bombarded with a neutron so as to get what? Barium and krypton. They are the most commonly cited products. Okay, there can be other products as well, but barium and krypton I'm taking, just imagine. And then during this process, the mass number here is 240, mass number here is 110, mass number here is 130, binding energy per nucleon is 7.6, binding energy per nucleon is 8.5, binding energy per nucleon is 8.4. They are asking you to find the energy released. How do you find this? This is binding energy per nucleon. So I'm going to find the total binding energy on the left side. What is total binding energy on the left side? 240 into 7.6. Why? 7.6 is the binding energy per nucleon. This is nucleon number, right? Mass number is also called nucleon number, right? Don't you remember? If I write XII, this is mass number. What is mass number to be precise? What is mass number exactly? Tell me. Mass number is the number of nucleons. Mass number is the number of nucleons. Number of nucleons. Number of protons plus number of neutrons. Mass number is the number of nucleons. Nucleon means someone who is sitting inside a nucleus is called nucleon. Okay. So protons and neutrons together. Protons are inside nucleus. Neutrons are also inside nucleus. So protons and neutrons are together called nucleons. This is nucleon number A. Understood? So how many nucleons are there? 240 nucleons are there. Protons and neutrons together. 240. One nucleon has this much. So what is the total energy then? 240 into 7.6. What about the right side? Right side I can calculate the total energy. 110 into 8.5. Okay. Here it is 130 into 8.4. Okay. So what is the total energy now? I'm going to calculate now. Just give me a second. 240 into 7.6 is 1824. 24 million electron volt. That is the total binding energy of the left side. On the left side. What is the binding energy on the right side? That is 110 into 8.5 is 935 plus this is 130 into 8.4 1092. So I am adding them up. 935 2027. This is 1824. You see a mismatch here, right? On the left side the total energy is 1824, while on the right side the total energy is what? Total energy is 2027. So what is energy released then? 2027 minus 1824. Look at that. Minus 1824. That is 203 million electron volt. That will be the energy released. So it's actually common sense because, wow, yes, whatever energy is on the left side should be same as that on the right side, because energy conservation should be there, no? So on the left side, when I calculate the total binding energy, I get 1824 only, right? 1824 only. While on the right side, if I calculate the binding energy here and binding energy here, binding energy per nucleon into number of nucleons, right? Total binding energy is a lot more, right? So when you take the difference, why is there a difference in the first place? Because right side, some energy is released as heat. Okay. So 180, 1824 is still there, plus how much is there? 203. That is lost as heat. So energy released is 203. Did you understand this? So what is mass defect? What is binding energy? What is binding energy per nucleon? You remember mass defect? I have few nucleons here. Look at that. I have few nucleons here. Now these nucleons are combined to form a nucleus. So these are protons and neutrons. Protons and neutrons. They are called nucleons, right? So I have protons and neutrons on the left side. These are together called nucleons. Nucleons. On the right side, I have a nucleus. They are combined to form a nucleus. XZA is my nucleus. XZA is my nucleus. So what is the mass of protons here? Mass of protons, total mass of protons. I could say Z times MP. Am I correct? Because Z is what? Z is atomic number, which is charge number, which is number of protons. Am I correct? Am I correct? Tell me please. If I write XZA, this is a nuclide for which Z is atomic number. Atomic number is also called charge number. Charge number is number of protons. So there are Z protons. One proton's mass is MP. One proton's mass is MP. So Z proton's mass is Z times MP. How many protons are there? Look at this and tell me, Z protons are there. Z protons are there. One proton has a mass of MP. So 2 protons will have 2 MP, 5 protons will have 5 MP, Z protons will have Z MP. How many neutrons are there? A minus Z, A minus Z. Why? Because A is the number of protons and neutrons together. This is number of protons only. So when you subtract, you are getting number of neutrons. So how do you get the number of neutrons? Total number of nucleons minus number of protons. So A minus Z. So A minus Z neutrons are there into Mn, mass of nucleon, mass of neutron. Now, when you take these together, you get the total mass on the left side. Total mass on the left side. And this mass is found to be different compared to mass of nucleus. Mass of nucleus is slightly lesser. Slightly lesser. So this mass difference is known as mass defect. Mass defect. So what is mass defect? When nucleons are weighed separately, weighed independently, and nucleus is weighed separately, when nucleons are weighed independently and nucleus is weighed separately, their masses are found to be different. This mass is slightly less than this mass. This mass difference is known as mass defect. How do you find it? Z times MP. For one proton it is MP, Z protons is at MP. One neutron it is Mn, A minus Z neutrons, A minus Z into Mn. So that is the total mass of nucleons minus mass of nucleus. Mass of nucleus is a single thing, no? So that will give you the mass defect. Difference in masses, mass defect. This mass is used for what? Used for binding the nucleons inside, binding the nucleons inside. How? As binding energy. So how do you find binding energy then? Binding energy is delta mc square, because energy is mc square according to Einstein's equation, principle of mass energy equivalence. Mass energy equivalence. According to Einstein's principle of mass energy equivalence, binding energy is written as mc square. So here m is delta m into c square. So there can be a numerical here as well. They'll give you Z value, MP value, A value, Z value, Mn value, Mn value. And then they'll ask you to find the binding energy. But remember, it's very easy. Only thing is, yes, you have to put the values and then find the difference. The answer will be in atomic mass unit, because mass of proton will be in atomic mass unit, mass of neutron will be in atomic mass unit, mass of nucleus also will be in atomic mass unit, AMU. So if this is in AMU, instead of multiplying with C square, you just have to multiply with 931.5 million electron volt. It's a standard value. Okay. So this is a previous board question, textbook question. We did this in class. If you remember, nothing. They'll ask you to find the binding energy. How do you find the binding energy? First of all, find the mass difference. Look at that. Z times MP. A minus Z into Mn. Then Mn, all these MP, Mn will be in atomic mass unit, not in kilograms. Do you remember what atomic mass unit is? 1.66 into 10 power minus 27 kilograms. So you'll have to do a conversion there. But instead of doing all those stuff, you could directly do that just by multiplying with 931.5 million electron volt or mega electron volt. This is actually what energy corresponding to 1 AMU. Energy corresponding that is found out in a standard method, right? By a standard method, 931.5 million electron volt. That's a standard value. Okay, so whenever 1 AMU, 1 atomic mass unit is converted to energy, this much of energy will be liberated. So you just put the delta M here in AMU and then multiply that with this. You will get it. And then they might ask you another question. Even though binding energy per nucleon is not there in syllabus anymore, you may have this question. You'll be given 2 elements like lithium and so it's 2 elements, and then you'll be asked to find which one is more stable. So you have to find binding energy per nucleon. How do you do that? Total binding energy. Once you found the total binding energy, divide that by number of nucleons, which is mass number, and then find out which one has greater binding energy per nucleon. That will be more stable. Did you understand that question? In one of the previous board questions, they were asking to identify the one which is more stable. You'll be given 2 elements. Right? Like lead and lithium or whatever you have, 2 elements, and you'll be asked to find out which one is more stable. How do you do that? You do this for the first element, this one. Okay. Do the same thing for the second element. That means you have to find binding energy for both the elements. But binding energy is not the criterion here. You have to find binding energy per nucleon, EBN, not EB, EBN. EBN stands for what? Binding energy per nucleon. How do you find that? Once you have found the total binding energy, divide that by number of nucleons. Number of nucleons is what? Number of nucleons is 8. Understood? That will give you binding energy per nucleon. Is that clear? Question number 25. Figure shows the stopping potential for the photoelectron versus lambda graph. 1 by lambda graph. For 2 metals, A and B, lambda being the wavelength of incident light. How is the value of Planck's constant determined from the graph? Okay. How is, if the distance between the light source and the surface of metal is increased, how will the stopping potential for the electrons emitted be affected? Justify your answer. Okay, let us see one by one. Figure shows. So let us draw the figure first. We have done this question in class, but that was with frequency. Here they have given lambda. No, 1 by lambda. So don't worry, it is still the same. Draw the figure and tell me when you're finished. A and B. Did you finish drawing this? Okay. So what is the question? Question number 1. How is Planck's constant determined from the graph? Planck's constant. Second one, if the distance between light source and surface is increased, how will stopping potential be affected? Justify your answer. Okay. So first question is what? How is Planck's constant be calculated? Will be calculated. You know, first of all, I am writing the equation. This is Einstein's equation for photoelectric effect. Do you remember? H nu 0 plus half mv square. The incident energy. You remember this equation? This is the only equation in the whole chapter. Okay. And I told you that time, if a numerical is asked, it's going to be based on this equation. This is called Einstein's photoelectric equation, for which he got awarded with Nobel Prize in 1917. I don't remember, 1915 or something. Right. Anyway, A photon is coming onto a surface. A photon is coming onto a surface and it is going in, it is digging an electron out. That is what photoelectric emission means, right? Photoelectric emission, do you remember? Photoelectric emission, do you remember? A photon is falling on the surface, the photon goes in, it takes the electron out and comes back, right? Okay, so what's happening now? The photon has 100 joules of energy. It actually spends like say 20 joules in taking the electron out, and 80 joules will be imparted as kinetic energy to it. Okay, just like when you eat food, a part is used for your energy and another part is stored as fat. Same way, the energy that is falling here will be utilized for two purposes. One, to get the electron out. That is called h nu 0, work function of the material. Another one as kinetic energy. So whenever a photon falls on a surface, the incident energy, the energy that is falling, is used for two purposes. One, to get the electron out. Two, to impart kinetic energy. So let's go back to this. That is h nu is equal to h nu 0 plus half mv square. I'll take it to left hand side. H nu minus h nu 0 is equal to half mv square. But if you remember, we wrote this half mv square as ev0. Hope you remember this. Do you remember this? Kinetic energy is same as work done. Work done to stop the particle. Kinetic energy. Work done is what? Work done per charge is potential. Work done per charge. Today morning I wrote this. Work done per charge is potential. Cross multiply. Work done will be Q times V. Correct. And since it is an electron, it is E times stopping potential is V0. That is what I have written here. Understood? I'm asking everyone, tell me please. See, the incident energy is h nu, that is used for two things. One is h nu 0, the other is kinetic energy, half mv square. This is going to the left side, making it h nu minus h nu 0 is equal to half mv square. Half mv square is ev0. I'm going to write this as hc by lambda 0, hc by lambda, because nu is 1 c by lambda, because I have to write in terms of 1 by lambda there, no? Minus hc by lambda 0 is equal to ev0. I'm going to divide everyone with E now. So hc by E lambda minus hc by E lambda 0 by is equal to V0. Why did I divide with E here? Because I needed to get V0 here. V0 is on y-axis. So it looks like what now? Y is equal to mx plus c, which is a straight line. That is why the graph is a straight line. Did you understand till this point? So what is the case here? I told you the incident energy h nu is equal to h nu 0 plus half mv square. H nu 0 goes to the left side. H nu minus h nu 0 is equal to half mv square. That is h nu minus h nu 0 is equal to half mv square is kinetic energy. Kinetic energy is same as work done. Work energy theorem says so. Work per charge is potential. Cross multiply. Work is equal to Q into V. That is E into V0. Charge is E. V is V0. E V0. And divide throughout with H. No. Divide throughout with T. Why do I do that? Oh, I'm making nu is equal to c by lambda here. C by lambda. Converting nu is equal to c by lambda. H nu is hc by lambda. H nu 0 is hc by lambda 0. Nu 0 is threshold frequency. Lambda 0 is threshold wavelength. Why did I do that? Because I needed to get lambda in terms of lambda and EV0. I divide throughout with E. Why? Yes, E comes here. Hc by E lambda, hc by E lambda 0 is equal to V0. Why did I do that? Because I needed to get V0 on the right side. Why? Why V0 alone? Because as you can see, y-axis has only V0. It's not EV0. It's V0. Understood? Now this equation looks like y is equal to mx plus c. What is in place of x? What is in place of x? 1 by lambda. And what is in place of m? Apart from x, what do we have? Tell me please. In place of x, the circle term, in place of x, we have 1 by lambda. That's correct. On x-axis, we have 1 by lambda. Tell me what then? In place of m, what do we have? hc by e. M is equal to hc divided by e. They are asking you to find the Planck's constant. So h will be what? Cross multiply me divided by c. So how do you get the Planck's constant? Put the slope here. Yes, put the slope here. Slope here. Slope can be found out by taking tan theta here. Okay. Do the experiment. Do the experiment. Draw the graph. Take a triangle. Take tan theta. That will be slope. M. Then electrons charge here. Then velocity of light here. If you put all those values, you will get Planck's constant. Did you understand this? I can write this h nu. So I've changed this 1 by lambda to nu. So what do we get? H nu minus h nu 0 is equal to EV0. I divide with E, h by E into nu minus h by E into nu 0 is equal to V0. That also looks like y is equal to mx plus c. So in place of m, we have h by E. M is equal to h by E. So Planck's constant will be what? Cross multiply m into E. In the question we did, that was m into E by c. But here it is with the nu. So it is h is equal to m into E. Did you understand this? So another question. So the same question was asked in ideal school last year in a model examination, and they were actually giving like half mv square here, half mv square. So whatever comes now, you can do that, half mv square. So you take it in terms of half mv square, that's it. Tell me h nu minus h nu 0 is equal to half mv square. Now this one actually looks like y, because on y-axis you have half mv square, right? Is equal to, this is mx plus c, and what is in place of m? It is h. So Planck's constant, slope is equal to Planck's constant, direct. M is equal to h. Understood? Look at the y-axis. What is on y-axis? Half mv square. So this must be y, right? And this must be c. C is this, and this is m. And c is actually work function. H nu 0 is work function. Hope you got this. Did you understand? And second question is very easy. They are saying like the source is moved. Source is moved. If source is moved, intensity changes, but stopping potential does not change. When source is changed, what is changing? I gave you two sequences. I'll explain this in the next class. I'm just writing down. You can just write intensity, number of photons, number of electrons, photocurrent. This is sequence number 1, photocurrent. Okay. Second sequence is frequency, energy of photon is equal to h nu, then energy of electron, work done to stop it, stopping potential. Write these sequences. I'll explain that in the next class. Intensity changes means number of photons changes. Number of photons changes means number of electrons changes, because one photon removes one electron. That changes photocurrent. Second is frequency. When frequency changes, energy of photon changes. Energy of photon changes, energy of electron changes. Energy of electron changes, work done to stop it also changes. That means stopping potential changes. Okay. And if you know these, you can write any, you can give an answer to any question. Here they say like, here they say like the source is moved away. Moved away means intensity changes. Intensity changes. But remember, stopping potential is in another sequence. Will it change? No, they are not related at all. When intensity changes, what changes is photocurrent only. If stopping potential is to change, frequency has to change. These are on different sequences now. When intensity changes, what changes is photocurrent only. But if stopping potential is to change, frequency has to change. They say like they are moving it away, moving the source away. This is the light. This is the window. Light is moved away means intensity decreases. When intensity decreases, photocurrent may change, but nothing happens to stopping potential. Hope you understood this. I'm winding up for the day.